Hi, folks. My name's Jeff Kotz, and I'm here today to talk to you about continuous probability distributions. Now, if you recognize any of these slides, it's likely that you also recognize this textbook from whence they came. It's Basic Statistics for Business and Economics by Lind, Marshall, and Wathan. If you've been following along in this series, that should come as no surprise. Moving on, if you don't have these slides, you don't have that textbook, hopefully you'll be able to gather something about the stuff I'm going to show you. So right now, we're talking about the things that we need to know. The things that we're going to cover today are properties of the normal distribution, so we can pick up where we left off last time. We'll talk about how to use the z-score formula. And lastly, we'll start to introduce the notion of how you can take a raw score to a probability or proportion, and how you can take a probability or proportion and go the other direction and find the appropriate raw score. This is the type of stuff we're going to be looking at for Chapter 7 to let you know. This is going to come in two parts. The first part is going to explain some of the theoretical stuff. The second part is going to talk a lot about examples and all the different types, and to reinforce the idea that you can take a raw score to a probability to a raw score. Now, that's something that's sort of evolved out of the years I've been teaching this topic, exactly how procedurally to take information so small as a raw score and get the answer that we need, and that we always have to go through calculating a z-score and using the z-score tables to find the area associated with it. A lot of times that part of the process gets messed up a little bit, but hopefully when I start laying out procedures, it will make a lot more sense to you. So where we left off in chapters, oh gosh, let's say 3, we introduced the notion of the empirical rule. Now, what the empirical rule says is that if you have normally distributed data, like this picture here, you can use a certain couple of cutoffs, 1 standard deviation, 2 standard deviations, and 3 standard deviations away from the mean, to help understand how frequently values in that distribution occur. For example, 68% of all values, of all respondents, of all things, whatever, 68% of all stuff is within 1 standard deviation below and 1 standard deviation above the mean. And that's what you can see right there where it says mu. That's your mean value, and then you can add a standard deviation or subtract a standard deviation. That's 68% of the data. And we talked about this. A 95% rule is 2 standard deviations, and practically all or 3 standard deviations gets covered at 99.7% as 3 standard deviations. So we've seen the empirical rule before. But right now, it lacks a lot of precision. It's great for shorthand estimates. If you know your data is normally distributed, it can give you an idea of how likely something is to occur, but it doesn't get all the precision that we need. Now, here's an example. So, as part of its quality assurance program, the Autolite Battery Company conducts tests on its D-cell alkaline battery. I'm going to go ahead and say that's an ABCD sort of thing. Hey, cool. But we find out that the mean is 19 hours. Then on average, batteries last about 19 hours with a standard deviation of 1.2 hours. Questions. About 68% of batteries failed between what two values? About 98% of batteries failed between what two values, and virtually all of the batteries fail between what two values. Now, that's to say, at some point, each of these batteries has a lifespan, and where it ends, well, that's how long it lasts. So it's its failure point, or how long it lasts. When we go ahead and use the empirical rule here, we can see that, number one, about 68% fall within 16.8 and 20.2 hours. That's just taking the mean and subtracting 1 standard deviation or adding 1 standard deviation. About 95% fall between 2 standard deviations, and practically all within 3 standard deviations, 15.4 to 22.6. With all of these, we're using percents. Percents are decimals. Decimals are less than 1. We can use percents whether we derive them empirically for empirical probabilities, or if we can actually demonstrate the normality of the data with the picture like here, we're able to take that to another step. Being that they're less than 1 in their percents, we can derive an empirical probability. We can use this for predictions based on how likely these certain values are going to occur. The connection between the proportion or percent that's here and the probability is a very crucial one. We're going to use those in continuous probability distributions, which is the crux of Chapter 7. The normal distribution itself looks like this. It's the bell-shaped curve. We've been discussing this now for a couple of chapters. The normal curve is symmetrical with two identical halves on each side. Theoretically, it extends out to infinity. Those tails are asymptotic. They never actually touch the x-axis, but they get very, very close. And if you have the mean, or if you have a normally distributed data set like this, you know that the mean and the median and the mode, all three measures of central tendency, are the same. They will divide the data in half, median, be the highest point, mode, and it will balance, mean. All three central tendency points are the same with the normal distribution. However, there's a whole plethora of normal distributions, and they can differ on a couple of characteristics. First of all, their standard deviation can differ, like we have here. We can see that they all have the same mean of 20 years of service right there, but for the one in red, the Camden plant, that's a very small, relatively speaking, standard deviation. Your standard deviation is small, 3.1 compared to 3.9 or 5.0. We can see that we end up with a narrow or leptokurtic distribution. It's leptokurtic, which means it's very peaked and pointed. Unlike the blue one here, which is the Elmira plant, it has a larger standard deviation, so it's much flatter. We call that platykurtic. Somewhere in the middle, we have the green curve. Its standard deviation is between the leptokurtic and the platykurtic, so we're going to call it the mesokurtic. It's somewhere between leptokurtic and platykurtic. Couple easy mnemonics for that type of stuff is that, well, first of all, meso starts with M and it's in the middle. All right, meso's in the middle. Platykurtic, plat sounds like flat, or you can think like a platypus, which is one of those flat animals with the beak and the beaver-like tail, and I think it lays eggs, but it's a mammal. Anyway, it's flat. So plat, flat, platykurtic is at the bottom. And then leptokurtic is the narrow one. Now, it's like you're leaping or you're jumping or you're trying to get up. Those are the three types of curves, the curves here. The big takeaway is this. The smaller the standard deviation, the narrower your curve. If you have a large standard deviation, your data is very spread out. But if you have a small standard deviation, your data is very close together, and you end up with a leptokurtic curve like the one in red here. Not only can they have different shapes, by the way, the only thing that affects a normal curve's shape is its standard deviation. Shape is determined by standard deviation. Position, however, is determined by its mean. You can see across the bottom, these three curves have different means. By their shapes, you can tell they have different standard deviations, but their position is determined by the mean. Or we can hold that shape constant and have them all have the same standard deviation, where the only thing that differs between them is their means, which determines their positions. I mentioned earlier that the crucial point of the percents being a decimal is that it allows us to make predictions, and it makes predictions about proportions. Well, in a normal probability distribution, like the probability distributions we talked about in Chapter 6, a lot of the same things apply. But in the case of a normal probability distribution, first of all, it's bell-shaped, and we've been discussing that about the normal distribution for chapters now. Two, it's symmetrical. Hey, that's a normal distribution property too. We've seen that before. It's asymptotic. We talked about that earlier. The mean, median, and mode are all equal. We discussed that as well. The total area under the curve is 1. Now, this is like saying that all possible probabilities that we can use the normal curve to predict exist. Everything that can possibly happen. Whatever point you select along the x-axis, that determines all possibilities. Their likelihood is the vertical distance. What's going to occur is across the x-axis. So all possible occurrences are under the curve. which is why the sum is 1. And the last one is a sort of a corollary of having a symmetrical distribution where the total area is 1. All the area to the left is 1. All the area to the left is 0.5. All the area to the right is 0.5. Now, these are properties of the distribution, and they're going to be pretty useful when we start doing examples. The standard normal probability distribution is so important. What it allows us to do is to take a data set, whatever that data set is, and convert it to a standard unit. Now, those units are z units, represented by the formula down there. Now, the standard normal distribution is a normal distribution, a bell-shaped distribution, where we define two things about it. One is that the mean of the standard normal distribution is always 0. 0 is in the middle. The standard deviation is 1. That's how dispersed or how spread out the data is. Once we define normally distributed data with a mean of 0 and a standard deviation of 1, we want to convert whatever data we have to that distribution. Why? Because it gives us a fantastic means of comparison. If I know that whatever my data set is, if I standardize it, if I put it in terms of z, and you tell me, oh yeah, the z-score was 0, I know you're talking about the mean. If you say the z-score was positive 1, I know that you're talking about something that is greater than the mean at a certain distance. If you tell me that a z-score was negative 0.5, I know that it's less than the mean, and by a small amount. These are things that we'll learn about the standard normal distribution. Defining the characteristics here, 3 is pretty important. And those were the z-scores I was just talking about. First of all, it is a signed distance. Signed means that it's positive or negative. Z-scores can have both positive and negative values. This isn't like probabilities where they can only be positive. Your z-scores can be negative if they're, well, talking about a raw score that's less than the mean. So the z-value is a signed distance between the selected value designated x. So we're going to use some x value. You're going to tell me some raw score x. And now I'm going to generate from it a signed distance. That signed distance is the z-score, positive or negative, and how far away. Its z-value is a signed distance between the selected value x and the population mean mu divided by the population standard deviation sigma. And that's the formula down there. That's it. There's only 3 parts to it. Well, the first thing I notice is that if I choose an x value that's the same as my mean, if x and mu are equal, if I subtract them from one another, or one from the other, I end up with 0 as the numerator for my z formula. 0 divided by anything is 0, given a non-zero standard deviation. But anything, a 0 divided by anything is still 0. So if I choose x as the same value as the population mean, the z-score is 0, which means it's not different from the mean. Second thing I notice is that if I have a, let's say, relatively large difference on the top. Relatively, how do we know? Well, relative comes from the standard deviation. So the relatively large difference on top could be a difference of 100. Let's say the mean for my particular data set is 100. I'm talking about IQ scores, where typically the mean is determined to be 100. And the standard deviation is, let's say, 15. Now, if I have a difference on top, someone has an IQ of 300, I don't even know how that would be possible. 300 minus the mean of 100 gives me a numerator of 200. Now, is that a big difference or a small difference? I don't know. I divide it by the standard deviation, and then it will tell me whether or not that difference is big or small. That numerator difference, whatever it is, if I divide by a big number, then that large difference is presumed to be relatively small. If I have that big number on top and I divide by a small number, a big number divided by a small number is still a big number. That thing I divide by, That's sigma on the bottom. Tells me how spread out my data is. So if I have a difference on top, whatever it is, and I have a small standard deviation on the bottom, whatever it is, any number divided by a small standard deviation is going to give me a big z-score. In sum, the sigma across the bottom that we divide by tells us about how dispersed our data is. If you have a small sigma, that means your data is not very spread out. That means most things are the same, or at least similar. And then if you have something that is very far away from the mean, it is not typical, because I determined typical to be small standard deviation. Therefore, a big difference divided by a small standard deviation gives me a large z-score, indicating that it is far away from the mean. It is a distance. Or if everything is, let's say, very spread out, our standard deviation is very large. It is typical for things to be far away from the mean, so it's a large denominator, a large standard deviation. Whatever difference I have on top, divided by the fact that everything's mostly spread out, is likely going to lead me to smaller z-scores, typically. So that what we might have thought was a big difference in another distribution, perhaps a distribution very narrow in terms of its standard deviation. A large difference there makes for a big z-score. A large difference where things are typically spread out, not a big deal, occurs quite frequently, in fact. These are properties of the z-score. The more you use the z-score, use this formula, the clearer what those properties are. That's why there's so many examples in part 2. If we wanted to do this particular example, to actually use the z-score, we can see how that works here. So here's an example. Weekly incomes of shift foremen in the glass industry follow the normal probability distribution with the mean of $1,000 and a standard deviation of $100. What is the z-value for the income, let's call it x, of a foreman who earns $1,100 per week? So we're going to say x is $1,100. And that's the first example we have right here. We put $1,100 in for x, put $1,000 in for mu, and $100 in for the standard deviation. We do the arithmetic, boop, 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 and then we've got a z-value of 1. That means that $1,100 is 1 z-unit, or 1 standard deviation above the mean. Above the mean? Yeah, because it's positive. It's a signed distance. $1,100 is 1 standard deviation above the mean. $900, on the other hand, is still 1 standard deviation away, but this one's negative. So we can have positive distance or negative distance from the mean. That's the basic z-score example here. Now we come back to this drawing which you talked about earlier, which was the empirical rule. Now look at that, we've got these two scales here. We've got a scale of x and a scale of z. Scale of x is in your raw units, your dollars, your hours, your peoples, your whatever those units are. That's what this is. So that $1,000 was the mean, the $1,100 is over here, $900 is over here. Those are all in the x units. I talked about how important it was to convert to z units. That's the standard unit. Well, that's down here. Notice that 0 is at the mean. That's the property of the z. And that we've got units down here, 1 standard deviation, 2 standard deviations. That 1 corresponds to that 1. That 2 corresponds to that 2. That -3 corresponds to that -3. In other words, when we convert things to z units, all we're doing is talking about how far away something is from the mean in terms of standard deviations. Sure, this is, if we go back to the foreman example, this is $1,000. We go over here and it's $1,100 because we've added 1 standard deviation. Well, why don't I just go ahead and say it's 1? Or it's -1 instead of $900. This could be particularly useful if, let's say, there's another industry like the steel industry, where we find a similar mean but a different standard deviation, or a different mean and a similar standard deviation, whatever the case may be. We can't expect steel workers to make the same amount of money as glass workers. However, within each industry, we can still say that someone who earns $1,100 makes more money than this many, whatever this number ends up being, 84%, makes more money than that many of his or her comrades. Where we go to the steel industry, someone might make more money in terms of dollar amount, but relative to their peer group, they might not make more money than as many people. Like we said, if someone is 1 standard deviation above the mean, they make more money than 84% of their peers. That's the reason that the Z unit down here makes for such great comparison between data sets. Z-values are more specific than the empirical rule in those things I was just talking about in terms of the 1s, the 2s, and the 3s and stuff. That the mean value of x will always have a z-score of 0. Scores that get a z-score, or rather z-scores bigger than 2, are a bit suspicious. And z-scores bigger than 3 are a bit strange. The reason is how different they are, how far away they are from the mean. They're not impossible, they're just things that might need some investigation. Similarly, z-scores less than -2, less than -3, same stuff. Now, z is assigned distance, how far away. The sign indicates whether it's above or below the mean, but ultimately it's the absolute value, or how far away from the mean we're investigating. This is another example that extends from the problem we were just talking about in terms of the glass factory foremans, foremans. So if I wanted to ask the question, all right, if I know that about someone who makes $1,100 makes more than about 84% of their peer group. By the way, that number is a number I knew. We're going to figure that out. You're going to figure out how to figure that out later. In the case of this question, we're trying to find the answer to what's the probability if I select one of these foremen at random that this person makes between $1,000 and $1,100. That's a question we might ask. Hey, we asked it. How do we answer this question, though? Let's think back to when we were talking about discrete probabilities. This comes from chapter 6. If we wanted to, let's say, determine the likelihood that between 1 and 3 flights inclusive would be late, all we'd have to do is add up the heights of each of these bars. Random variable x across the axis, indicating 0 late flights, 1 late flight, 2 late flight. The height of each bar determines the probability. Well, because it's discrete, I know I just have to add up 1, 2, 3 things. I add up those 3 things and I know the probability of a certain range of late flights occurring. And I can do that because it's discrete, because they're just squares and they have heights, and I just add up 3 things. But I can do it because it's discrete, not continuous. Continuous, I don't have individual bars that I can measure their heights. What's a boy to do? As it turns out, you just make those rectangles very, 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 very narrow. So narrow, in fact, that a smooth curve can fit under them. It's called calculus, folks, and that's where this comes from. Now, we're not going to get into the calculus because I want to use it for the probability aspect, but suffice it to say, changing from discrete to continuous is a matter of integration. So we found the z-scores for all of these values in the previous example. I know that this is a 0 and this is a 1, so really I'm trying to find the area between z-score of 0 and the z-score of 1. The standard normal probability distribution has a definite shape that does not change. Its mean is 0 and its standard deviation is 1. Standard deviation determines the shape of a curve. Because the shape does not change, given any 2 points along the bottom of the curve, I can find the area that fills up between those 2 points. Even with this weirdo beautiful looking curve up top, I can do that too, because that weirdo looking curve is always shaped exactly like that. We have to use a table to find these answers. Well, we don't have to. We could do the integration and the calculus and do it that way. I don't have time for that. Or two, we can do it in Excel, and I definitely have time for that. But for this third example, we're talking about the way those of you who have me for class might likely be seeing on an exam, and that's using this Z table. The way you use this Z table is to first note that on the outside or the axes, that's the Z values. Over here we have the whole number first position as well as the decimal for the tenths spot. Across the top, we have the hundredths spot. This is an abbreviated table because there's no 0.09 over here. Would go down below 1.8 there. But to use this table, let's say we wanted to find the area between 0 and 1. Well, this table always starts at 0. It always says that one of the boundaries is 0, and I'm going to the right, to whatever z-score you decide to select. In this case, I'm going over to 1.00. First, I find 1.0 on the left. There we go. Second, I find 0 across the top. 0 is the hundredth spot. I find out where those two things intersect, and right there, 0.3413 is the area between z equals 0 and z equals 1. In other words, the area in that range between $1,000 and $1,100 is 0.3413. That area is the probability. That area is the proportion. This means that there's a 34.13% chance that a foreman selected at random will have a weekly income between $1,000 and $1,100. You go back to thinking about the beginning, call back to the arrows. We started with the raw scores of $1,000 and $1,100. We started with raw scores. We converted those two raw scores to z-scores, a z-score of 0 and a z-score of 1. We used those z-scores to find the area under the curve. We used the z-scores on the outside of the table to find the area under the curve. All of these decimals inside the table all indicate areas under the curve, which is good because they're under the axis. They're under that curve. It's straight, but whatever, it's under there. All those things under there. Under where? Yes, under there are the areas. The outside indicates the position. So we take the raw scores, we convert them to z-scores. We use the z-scores to find the area. That area in here is the probability, is the proportion. Because 34.13%, that proportion is under the curve there, that's also the probability because the area under the curve is 1. So 34% are between there, and that's also its probability. I'll use probability and proportion to mean the same thing quite frequently. So that's going from raw scores to probabilities. Hey, we just got there. If we didn't want to use the table, we could use Excel. And there's a couple of different Excel functions. This one here is normdist. I also believe normsdist might also work, or norm.dist. There's a few different values, or a few different functions. They all basically have the same arguments, which is I need an x value, I need a mean, and I need a standard deviation. In some circumstances, you might find a cumulative property, or you just find a not cumulative. You're just doing forget what the term that Excel calls it. They have different terms. But generally speaking, you want to do a cumulative anyway because you're looking for areas. So that's how Excel does it. But when we do it in class, there's pretty specific procedures that I want people to follow. The first step, always draw the picture. I want you to draw a normal curve. I want you to draw something. It doesn't have to be perfect, but it needs to have, let's say, 4 elements. First of all, it should have a curve. Second of all, have an x-axis. Third, it should have the line that marks the middle. Fourth, you can draw the mean in here. So make sure you have all those points. Start by drawing the curve. We got to draw it every time because there's so many different scenarios that we're going to be converting to standard normal probability distributions. Yeah, I'll show you. So the area under the curve, we always use our Z table, and that's where you're going to have to do it, I think, for exams as well. Yeah, I know for exams. The area under the curve is always the area between the mean and whatever Z value you select. Always between the mean and the Z value, or the X value, X you convert to Z. However, there are so many different scenarios that you can get them pretty easily confused. We just saw an example of, all right, we've got one value is the mean, the other value is, some standard deviation away. That's fine. I know how to calculate that. That's the number the table gives me. Well, we might have to go to the left side of the axis and know that we're subtracting the standard deviations, not adding them. Maybe we want to find the area just in this little tail, not the body. Maybe we need to get this sliver between two chunks. The textbook, the table is only going to give me that amount as well as that amount. In other words, the area captured between 0 and 250 and the area between 0 and 150. In order to find this sliver, we need to subtract them. Or, heck, we might have some on both sides of the mean, but we have to use different z-scores for each side. It's absolutely wrong in this bottom example here to say I could just look up 3.6 in the z-table because 1.6 plus 2.0 is 3.6, and that's how many z units are there. Absolutely wrong. Don't do that. We need to calculate each side on its own because of the shape of the curve. Sometimes we'll even be given a proportion, and that proportion cuts off a certain portion of the tail, and I want to know what x value or what raw score will determine this proportion. That's a circumstance where you start with the proportion and then you have to work backwards to find this area. That area we use to calculate a z, and that z we use to calculate a raw score. So sometimes we go from raw scores to probabilities and proportions. Sometimes we use proportions to determine raw scores. We can go in both directions. If we want to go from a raw score to a probability or proportion, always draw that curve first. Write the process, write this thing out so you know what step you need to do, and draw the curve. That's so important on every problem. Just get into the habit of doing it. It'll keep you in the mindset of, I know what I need to do next, I know what I have, and so on and so forth. So write the process, draw the curve. Second, or third at this point, you extract the essential information from the problem. What do you have? Do you know x? Do you know mu? Do you know sigma? What sort of information do you have? Label what you can on that drawing. So if I know the mean is 43, I should put 43 right here because I know it's in the middle. The other pieces of information, for example, x, we should put relative to the mean. If x is 40, we should put it on the left side. If x is 49, we should put it on the right side. Left and right tells us direction. Z is a signed distance. That sign for Z is so important. If it's on the left side, Z is going to be negative. If it's on the right side, Z is going to be positive. It's important to label all that information on this drawing as you can. The next step is to convert those raw scores to z-scores. If you use the z-score formula, you put in x, you put in mu, you put in sigma, and now you've got your z-score. Label the z-score along with wherever you put your raw score. It should be easy for the mean should be easier than easy for the mean because the mean's always 0 in terms of z-units. Once you have that, once you've got the z-scores on your drawing, you can use those z-scores to go to the table and find areas that you need. Again, in some circumstances, it may be as easy as finding one area. Maybe you recognize it's on the left side and you got to do that. Maybe you got to subtract something. Maybe you've got something on both sides. Whatever the case, you've now got the z-scores, and the z-scores are the things you need to calculate those areas. Calculate the areas, look up the areas. You use the z-scores to look up the areas. And then the last thing you do is you take that area that you've looked up and do whatever computation you need to do, whether it's subtracting them like this one, adding them like this one. Maybe you take this sort of complement thing, 0.5 minus it, sort of complement thing. Not exactly complement, but sort of complement. But use those areas to answer the probability proportion. Again, sometimes you have to add them, sometimes you have to subtract them, but once you get that far, most of the work is done for you. Alternatively, you may be given a probability of proportion and asked to find the raw score that cuts that off. Always draw that first. Write the process, draw the curve. Write the process, draw the curve. Write the process, draw the curve. Extract the essential information and label what you can on the drawing. As it turns out, those steps are the same almost always. In this case, instead of labeling stuff across the axis down here, you're likely to draw one of these lines and write in the area that's there. Or if it says, let's say, cut off the top 5%, you're going to draw some line over here, say that 5% of the area is in the tail that you cut off, meaning 45% is between the mean and where you cut off the tail. Label what you can with your given information. Next, color in the area that represents the proportion in question so you know what you're looking at on your drawing. Use that area to go backwards out of the z-table. For example, if in this example we were looking for an area in the table of 0.4332, we might need to find that area. Sorry, we look for an area. We do our drawing. First, we draw the curve. We write the process, draw the curve. Say that we're trying to find 43% of the area in here. So in our drawing, we've written 0.332. We would actually find that number in the body of the table and then go backwards to find out the z value that's associated with that area. Once we find the z value that represents your area, don't forget to attach the plus or minus sign. Sorry, please remember to attach a plus or minus sign. Once you have a z-score on there, you can use the z-score formula again. You put the z-score on the left-hand side, fill in mu and sigma on the right, solve for x, boom, you're done. Now you've got the appropriate raw score. Sometimes you have to find one, sometimes you have to find a range of values, whatever the case. This is the process if you're working backwards from a probability and proportion to a raw score. That's why you draw the picture every single time. What we've covered today are properties of the normal distribution, how to use that z-score formula, knowing its essential elements, and this process of taking a raw score to a probability or a proportion, or taking a proportion of probability back to a raw score. That's it for the first half. Going forward, come back for chapter 2 and we'll talk exclusively about examples, about how to use these and all those different shapes of those bell curves with things that got covered in. So I'm not going anywhere, but I kind of am, and I guess I'll see you around. Bye.